Juan Ramos, and I'm here to present the search and rescue robot. These are my partners, Dustin and David. As you can see here, we're going to be participating in the RoboCup competition. This competition is an annual international event that pits robots from all around the world into a disaster environment to go in there and find the simulated signs of life. Our introduction is basically centered around what we're planning to do for the fall semester, and this is in particular to build a robot that works and has a redundant algorithm which helps find signs of life. The motivation for this is we feel the robotics is exploding, and a lot of individuals are considering a lot of situations where they actually utilize robots, not only in industrial situations, but in other situations, and search and rescue is one such situation. The rules are going to be covered by my partner, Dustin.
All right, some of the rules to note here for our competition. Our robot's going to have to operate in a simulated urban disaster environment to look for victims, possible survivors. We're going to have to do this detecting more than one sign of life. Some possible ways are with like a temperature sensor, a camera for motion, a microphone for speaking or something like that. Another thing is we have to communicate wirelessly with our robot. Also, they don't necessarily say it's a specific rule, but smaller robots do have advantages because they'll be able to access other victims through like nooks and crannies and take other shortcuts. Some of the arenas to note, the first arena we'll encounter is the yellow, which is kind of like the qualifying arena. We do score points here only if our robot is fully autonomous in detecting the survivors. And it has 3D mapping challenges here where we'll have to like map out QR codes or things like that and relay information back to the user. The orange, it starts getting a little more complicated. It brings in stairs and pitch and roll ramps. The red arena is going to be the most advanced mobility here. It's going to have piecewise flooring, which is going to simulate rubble, other things like that, that the robot may encounter in a disaster environment, and uneven terrain. In the blue arena is the first arena where we'll get to use our manipulator arm. It's to simulate having contact with survivors. Also, we can use it to open doors and other shortcuts, so it's like a big must in our competition. The next arena is the radio dropout. Here, again, we have to be autonomous to simulate if something were to happen and how our robot would behave on its own, make its own decisions, things like that. And the black arena is going to be the most challenging one. It's going to be the most accurate, I guess, or real simulation of a natural disaster like a tunnel collapse, something like that. Some of the standards we'll follow for the 8020, which David will tell you about later, is with the DIN 17-615. With Wi-Fi, we're going to follow IEEE standards 802.11, and the RoboCup actually follows its own standards using DHS, NIST, or ASTM. David's going to tell you some more.
All right, I'm here to talk to you about the design and engineering of our robot. There are 4 major design components which we are implementing into the design of the robot. The first is the platform, which consists of the housing and the drivetrain of the robot. The housing encapsulates all the other components, the electronics, the sensors, the microcontrollers and everything, and the drivetrain is actually providing mobility to the robot. The second design component is the manipulator arm. It's just a standard robotic manipulator arm with a gripper end effector that will see most of its use in the blue arena, but can also be used to open shortcuts, as Dustin mentioned, in some of the other arenas. The third major design component is the electronics, which will provide the power to all the microcontrollers and sensors and motors and everything inside the robot. And the fourth design component is the systems that we're using, the sensors that we're using to try to find signs of life, and the algorithms which we will use to collect sensor data and relay it back to either the user or to the microcontroller. The design of our platform is going to be, the design of the drivetrain, is going to be 4 continuous treads that will be at each corner of the robot, and they will be able not only to move the robot forward, backwards, and turn, but they will also be able to articulate upwards and downwards in order to ensure that we'll be able to climb stairs and to get over some of this rocky terrain that the robot will be seeing. We will also incorporate an advanced suspension system into the drivetrain, which will minimize the effects of vibrations that would be given to the robot by uneven terrain and any debris that it might encounter. We will also incorporate a remote control assembly where we will be able to communicate with the robot and the robot will be able to communicate with us. The housing of the robot will be made out of this material. It's called 80-20 aluminum. This aluminum beam is very special because it actually has these patterns cut into each face of the beam, and these patterns will allow us to slide fasteners in there, and the fasteners are just a simple nut and bolt that we will be able to assemble and disassemble using only an Allen wrench. And this is very important to our design because we want our design to be very modular. That means we can assemble it and disassemble it very easily, very quickly, and without too much effort. And the design of the 80-20 allows us to do so. This is a very basic rundown of the control system that we're going to have searching for survivors in our arenas. At the very bottom, you can see the sensors that we'll use to look for survivors. These sensors will feed information to the master computer, and the master computer will relay that information to the users, which is us, and we will be able to relay the information as to where we want the robot to go, and the master computer will be able to give that information to the motor controller. However, there are arenas where we actually have requirements to not interact with the robot, in which case we will sever that user connection block that you see there on the side. Next, I'm going to talk to you about the manipulator arm. This is a 4-degree of freedom robot arm, very similar in the basic design to this toy that you see here on the left. It's powered by 5 servo motors, one that will allow it to twist the base, and the next set of servos will allow it to move around up and down and to grip with its grip or end effector. Ours is a lot bigger than this toy, of course. Also, we will mount some sensors onto the housing of the end effector, which will allow us to kind of look around with the sensors. We are going to use a coil spring suspension for the drivetrain. This will allow us to customize the level of shock absorption that the suspension system has, just by varying what the K value, the spring constant of the spring that we're going to buy is. This solution is very inexpensive, it's very low maintenance, and it's very reliable. People have been using it for generations. Why mess with perfection?
I'll be covering the economic aspect of it. As you can see from projections, that they're expecting it to be about $67 billion by 2025 because of robotics. So there's a lot of money to be made in terms of the skills that we learn here. And we all know that robots in general have the same idea, you just prep them for different situations. This experiment so far and working together as a team has brought several pitfalls, and at the same time we've learned from these pitfalls. We realize that we need to keep learning because what we learn in the classroom is only the basic theory, the basic idea, and a lot of things happen that which you don't plan for, and you have to basically work on the fly. So this taught us to work not only as a team, but better as engineers. Global awareness and the global aspects will be covered by my friend Dustin.
All right, some just key things to note that we want to take away from this. It is ethical to help victims in natural disasters, and we're going to enter like a overseas competition, international competition, so we want to observe proper sportsmanship. Some other perspectives here, we have to be aware that there are electrical differences as well as other differences outside of USA. We need to overcome these. In our transformer, we'll probably just have it able to use all the different powers. Technology is becoming smaller and more powerful, so we're hoping that it can be like widely accessed everywhere. And human growth is growing into more disaster-prone areas, so the need for this technology is becoming more and more important. We have collaborated with other countries so far. We talked with someone from Australia as well as other schools from America like Carnegie Mellon. The main goal here is we want to work together with everyone around the world to help people that from natural disasters. Thank you.
All right.
Thank you. Any questions?
Okay, I'll start it off.
Great.
Good morning, gentlemen.
Morning.
Nice presentation.
Thank you.
Thanks.
You mentioned that you want a modular design. Why?
Okay.
What are the advantages and why do you want a modular design? What does it-
Well, a lot of these specifics of the arenas aren't revealed to us until we are actually at the competition. So we need to be able to, on the fly, change some of maybe the positions of the sensors, maybe the positions of where the attachment of the manipulator arm is, in order to be able to meet these challenges that are right, in front of us, without us having to go back and redesign the entire machine. Also, it adds a level of interactivity that we can have with the robot outside of the competition, in case if this design actually works very well and it does need to be implemented in real disasters, we can change the design very quickly.
Thank
And
you.
to further expand on his answer, we're seeking to make it deployable anywhere in the world when a disaster happens, for example, an earthquake in Japan, or an earthquake or a tsunami in another country. We want to be able to get a robot, get to as quickly as possible, and make sure we can assemble it on the spot. And sometimes you're going to have chaos on the floor. You have first responders from different teams, and when a government situation jumps in, they say, okay, well, the Red Cross is here, we have our government forces here, and we have random civilians who want to help. And there's very, very little cohesion there. So you want to be able to have a system that's very simple to design and say, okay, this is what you do. You have a handbook, and when it comes to these disasters, we've read that usually simplicity is key. So,
Thank you.
Could you summarize the cost, the division of labor, and the scheduling, and with regards to the scheduling, are you on schedule?
actually, yes, we're ahead of schedule, to be honest. We've already made plans to begin to build the body, and the first thing we're going to build is the frame. Once we start doing that, we're going to start building the drivetrain, and in the fall semester, we're going to just basically hash out the programming, which will be done predominantly by David, but we'll help out with that as well, because we cut the task into different sections that match your strengths. And as far as the cost, most of the cost is actually going into the body itself. A lot of the sensors, they vary in prices, so we can select, we can play around with the sensors, but when it comes to the body, the prices are very set for the 80-20, and the threads are very expensive as well, especially if we want thicker threads. When it comes to the size does matter in this case because it gives you a larger footprint. So if your robot begins to lose, for example, traction in one set, you have 3 more sets. And the larger they are, the easier your robot can actually maneuver the field.
And division of labor?
The division of labor, the lead designer would be Dustin. He's actually working predominantly on the...
I'm gonna work on the platform mostly, and like the suspension, the tracks, things like that.
The electrical portion will be handled by me, and then David will do most of the programming.
Yeah, you've got a lot of moving parts, so there's obviously going to be a lot of vibration. To what extent have you incorporated in your design means to attenuate the vibration aspects?
Well, just with the suspension, basically. I mean, we're hoping that since we're using the 80-20, that we can secure all our sensors pretty well onto it and minimize like vibration just with the suspension.
Right, the 80-20 itself has a design so that when you actually do attach a nut and bolt onto it, it's not just a flat piece that it's kind of gripping onto. There's a slight, I think it's a 2-degree, I don't know what you would call it. It's not 100% straight. It's kind of curved, so that when you attach the bolt onto it, the bolt actually kind of, or the nut actually kind of bends a little bit. So it has a very strong grip onto it, right?
So you're relying on elasticity to attenuate your vibration.
That's a portion of it. To expand on the answer, we actually are going to have an advanced drivetrain. They mentioned earlier we're going to have a coil spring suspension system, and that's going to be for each individual portion. So we have 4 different continuous tracks. We're going to actually modify each of those so that they actually deal with the suspension. So we're going to use actually some of the stuff we learned in system dynamics to actually model that and be able to absorb any of the extra energy. And similarly, in case we have a situation where the robot loses power suddenly there, the others don't struggle too much to actually remain with the power. So we're happy to use that suspension system for that purpose.
Thank you.
Any further questions?
Yeah.
Great. Thank you again.
All right.
Thank you, everyone.
Keep it up.
Thank you.